Okay, now let's talk about the AC source, or we can call it one of a time-dependent signal source. The time-dependent signal source means that it depends on the time. It's not constant, or it's not direct current source, right? Not DC. So it's changed in according to the time, and it's usually in the AC circuit the source is changed in periodic nature. For example, in sine wave, usually we have sine wave signal for AC circuit, right? So mostly we talk about this kind of signal, okay? And this type of signal will come in periodic characteristic. So the signal at time t will equal to the signal at time t plus n capital T, where capital T is the period of xt. Okay, it's come back to the same value in every period, right? In this for the period capital T, in this case, it's come back to the same value in every period, right? In every period, like this. And so we call this is a periodic signal, or in the electrical AC signal is the alternative current signal. Okay, and then we can represent this type of signal in this form, right? In cosine form, xt equal to a cosine cos omega t plus phi. Phi is the phase angle of that signal. So if phi is 0, so the signal start from 1 at time equal to 0, right? Because it is the cosine function, and the omega is we call omega as a radiant frequency, or is the angular velocity. We can call it angular velocity or radiant frequency. It's 2 pi f. F is the frequency of the signal. So how many cycles in a second, right? In this case, and this is the periodic signal here, right? And if the signal have a phase angle is the phase shift. In this case, phase shift here, the phase shift in phi here. Okay. Anyway, mostly in the practice computation in AC circuit or in AC electrical signal, we don't calculate in this form, but we will calculate. Mostly we calculate this type of circuit in phasor by phasor analysis. So I will use the phasor analysis in this topic mostly. Okay, so I would like you to understand how to solve the AC circuit in phasor analysis form. So from the periodic signal, it will change to phasor form. So in phasor form, it will be, or we can say it's in the complex value or vector, or in vector form, right? So in this case, the periodic signal will represented by the complex form. In this case, this will be fine here. And this is RMS value is E divided by square root 2 here. In our calculation is we will represent x2 by x2 in phasor form is will be A divided by square root 2, which is RMS value with the angle of phi here. Or in complex value, it will be A divided by square root 2 cos phi plus G sine phi. Okay, this is the complex value. And in electrical calculation, this type of value, for example, C equal to 3 plus 2i. Usually we write in this form, 3 plus j2 in this form rather than this form. Okay, this is in similar way, right? And I is square root minus 1, or in this case j is square root minus 1. So we just use j instead of I, because we avoid confusing in using I as a current, right? I usually we use I for represent the current, right? Mostly in the circuit. So for electrical engineer, we use J instead of I in complex number. Okay. Okay, and the AC value, we will have one value to represent the energy dispatch of AC waveform. We call this value as the RMS value. So we represent the amount of the signal by root mean square value. And root mean square value can be computed by this. This is average value, sorry. This is average value. It's not the same as average value. The average of AC signal is 0, right? We have positive and negative. If you cancel each other, the average signal of AC is 0. So we don't use average value in computation, but we use the RMS value here. RMS value here. Okay. So this is the RMS value, or root mean square value. And in this case, we just make a square root of the sum square, okay, or of integration, one cycle of one cycle. So we always have this value in positive, right? It's not equal to 0. It will be more than 0 in this case. Here. Or this value may called effective value. It will equal to the DC power or DC source that's to represent this AC source. For example, if we have the signal, maybe the peak is square root 2 with 220 volt, and we have DC source of 220 volt. These two sources will supply the same energy to the same load. Okay, if we connect this source to one load here, for example, resistance, this is square root to 220, and this is the DC source of 220 here, right? And sorry, this is 2 square root to 220 cosine omega t, like this here. This will be it will make this resistance absorb the same energy. This is will have the same energy equal to each other. So for the sinusoidal function or sine or cosine wave function, the RMS value is the peak value equal to the peak value of maximum value divided by square root 2. Okay, and then this AC signal, we call this signal is 220 volt. This is mean RMS value, right? RMS value is the peak signal divided by square root 2 here, right? So this in fact around about 311 volt, for example. 311 volt will have the RMS value of 220 volt and 50 hertz, for example, here. Okay. So here is what I have explained. So the the power absorbed by the resistance equal to I square R. So in this case, it's equal to the RMS value. Okay. So in for sinusoid waveform, sinusoidal waveform, or in cosine or sine waveform, right? If we take this formula to find out the RMS value, finally we will get the RMS value will equal to the peak value divided by square root 2, right? Here this is the peak value. So the RMS value of this x1, right? x1 RMS value equal to then by a divided by square root 2 is easy to get the RMS value. So instead of you solve from this equation, we don't need to solve by this equation. We just divide the peak value by square root 2. Okay, so we call this as RMS value. And when we on the other hand, if we have the information, for example, voltage is AC 220 volt, 50 hertz, we know that in fact the waveform is in this shape, right? The waveform will be have the peak of, right, square root 2 into 220, right, or 311 volt, and 50 hertz mean the 50 cycle per 1 second, or the waveform voltage, this shape will be square root 2 into 220, and then sine 2 pi 50 t, right, as a function of t here. So we get this waveform. Okay, but when we make a calculation, usually we just use the RMS value 220 volt, and with the phase shift, if you have the phase shift, you add the phase shift here, right? The phase shift will be in the to make the vector have some angle from the reference axis. Okay, here. So what is the peak voltage of AC sinusoidal? 220 AC, right? It will be square root 2 into 220, right? Here, right? This is the peak voltage here, right? Because the VRMS equal to V peak, right? Divided by square root 2. If we know RMS value, we know peak value, right? Okay. So now this type of signal will affect to the storage device, because it's changed according to the time, right? Last time I talked about the storage device, which are the capacitor, right, like this capacitor, and inductor, right, like the coil, like this. So this type of device will act to the rate of change of the current and the voltage. So this type of signal will make some mostly effect to the storage device here, right? Here. For example, if we have the capacitance in the circuit, it will have we can form the to solve this type of circuit will be complex, and we have to solve in the form of differential equation. For example, if we just have the KCL here, right? KCL here. So we have the current flow in this is not KCL, right? This is IC, and this is maybe KVL here, right? KVL here, like this. Or in this case, IR1 equal to IC, for example. And if we make KVL here, V source minus VR. VR is I into R, right? VR and I, this is IR or IC, this is equal, right? Or VS minus IR or IC into VR. And then what is this voltage? This voltage is CdV by dt, right? C di by d C di by dt, right? So then it's minus C dic by dt, right? This is, oh sorry, this is R1, so this is R, right? This is R. IC into R, right? This is VR, this is VR here, equal to 0, and we can rearrange this equation into this equation, right? dc by dt, dic by dt plus we divide the equation by R and C, right? And R and C. Then we got 1 by, oh no, sorry. dvs by dt. Oh, sorry. C dv by dt. Vc. Sorry, I confused something, but anyway, okay, let's see this equation, right? IR equal to VS, VS minus VC, right? And divided by R and equal to IC, and IC is C dV by dt, right? IC is C dV by dt, and we just rearrange this equation here, right? This equation, we get this equation, okay. But anyway, I just would like to show that we need to solve the differential equation like this, and we need to use the techniques for ordinary differential equation. If we have one solid element, the equation will be first order, right? First order differential equation. If we have two solid elements, we have second order differential equation, and that you learn in mathematics or calculus 3, right? And it will be very complex, and in fact it will be in the next lecture for tangent circuit. But as I told that maybe this part I will skip that topic, and I will start the magnetic circuit from next time, okay? But anyway, for the phasor analysis, we don't need to solve this type of equation. So I think maybe you become happy, right? That you don't need to solve this type of circuit, but it's not so easy to solve as well. But we can use the phasor techniques to solve this type of circuit, okay? So for AC circuit, we will transform every element into complex number, right? Instead of showing signal, right? This is a signal, right? But we can transform the signal form to complex number form. Complex number. And we can analyze the complex number into two representation. So this is we call polar form, right? In polar form here, and or we can use the complex form, right? For example, A with the angle theta, we can write down the voltage in phasor form or polar form in A with cos theta plus J psi theta, right? This will be in complex form, right? In complex form, right? Real and imaginary part, right? We have real part and imaginary part for in this case, and in this case we have magnitude, right? Magnitude or absolute magnitude, and phase angle, right? Phase angle here, okay, for the AC circuit. Okay, then for the voltage of Vm cos omega t plus theta v, right? We can represent the signal in this form, right? Vm with theta v, and the current also plus theta v, right? In fact, for the RMS analysis, this should be divided by square root 2. This is also divided by square root 2, okay, and it will be in the complex form, right? Complex of polar form. This is absolute V 2 like this. Okay, and then when we have the source in phasor form, the load can also be represented in phasor form, right? And for the resistance, it will be just the resistance, because so in this case the resistance would be the resistance, and the voltage in phasor form and the current in phasor form will have the relation similar to Ohm laws, right? The resistance would be the resistance. It's just a real number, no imaginary part, right? Just real number. Even voltage will have both real and imaginary part. The current also will have real and imaginary part. This is a, if the voltage, so the resistance will have only real number. In this case, the voltage and current will have the same angle, right? We have the same angle in this case. But for the inductance will shift the current and voltage by 90 degree, and it will make the current lag from the voltage for 90 degree. And the formula is the voltage and the current will have the relation by j omega L with the inductance value of L, with the inductance value of L. If you substitute the relation into the sinusoid signal, we will have that the voltage and current will shift each other by 90 degree here, right? Shift by 90 degree. It will shift by 90 degree, and the current will lag the voltage by 90 degree. If the voltage have the angle plus 90, the current will have the same, just the angle here, right? Okay. The value that make the phase shift is here, right? J is will shift the phase by 90 degree. Okay, and for the capacitance will shift the current and voltage to each other by 90 degree also. But for the capacitance, the current will lead the voltage by 90 degree in this case, right? Okay, I will show the summarize of the formula later. Okay, and this is the value that make the current lead the voltage by 90 degree, right? Because the voltage is will be I divided by omega c, and with or we can say this value is I divided by omega c with 90 degree lag, right? And the voltage lag current by 90 degree for the capacitor. Okay. And so for the any element, usually we don't have the load or the equipment in the industrial or in the building or in our home with only resistance or with only inductor or with only capacitor. We will have the mix up together of the different type of load or of the equipment. For example, the motor will consume the current and voltage that can be represented by the sum up between resistor and the inductor, right? For motor have both resistor and the inductor, so we call this value as impedance value. The impedance value is the value that will act to the voltage and current in accordance to its amount and phase shift. So if we have the voltage supplied to the impedance, for example, in this case, this is an AC circuit. We have V with the phase shift of theta V here, right? And this is, we have the impedance. The impedance is the mix in between resistance and the X value. X value, we can call X value as a reactant value right here. Reactant value here. And R plus JX we call impedance value, and the inverse of the impedance we call admittance value here, right? And the relation between voltage and current flow is V equal to C into I, right? And impedance, we use the symbol C, right, for impedance. This is similar to, this is AC circuit, right? AC circuit. And it's similar to the Ohm laws of DC circuit. This is only pure R, right? DC, like this. And instead of using resistance, it's become an impedance in this case. Okay, so each equipment will have its impedance, and the impedance is depend on the frequency of the voltage also, because omega is the, right, 2 pi f. So if the frequency is changed, the impedance of the element is also changed also. But for this common practice system, usually the frequency is constant, right? For example, 50 Hertz or 60 Hertz. Therefore, the impedance can be represented by the constant value, right? This is constant value, but in complex value form here. Okay, when you solve the AC circuit, so you need to solve in the complex form. Okay, so but anyway, this AC circuit, I will use the circuit not so complex as the DC circuit, right? Okay, yeah. So when we add up the two elements together, we just add it in the same way of the resistance circuit. Okay, yeah. Okay, I think I will skip this part and come to here. Okay. Okay. I think I should make some example on the phases analysis, right? So if we have the voltage connected to the impedance C, and this is voltage, this is the current I, right? So for example, voltage may be 220 with the 0 phase angle, and the impedance is 3 plus J2, for example. So we can compute the current I by this formula, right? V equal to C into I, and it will be 3 plus J2 and I, and this is 220. Okay, and so the current would be 220 divided by 3 plus J2, like this, and you need to solve this complex value into the complex value. Okay, how much for the current, right? It will come out as a complex value, right? As a complex value, right? I think you can solve this type of complex number, right? So if you forget some complex number theory, so please remind you again. But I think maybe your calculator may help to solve this problem as well. Okay, and then when we have complex value of voltage and current, the power in complex number the power of the we call complex power, or the power of AC circuit, right? It's the power of AC circuit. It can be computed by the S equal to V into I, and then V is complex value, I also complex value. Therefore, S will be a complex value. So we have the power in complex form. What mean by power with a real and imaginary part? It's not only real part. What is the physical of the power with imaginary part here, right? So S is V into I. So it will be EV and I with theta V plus theta I, right? Here, these two values multiply together. So we have the power with phase angle, right? So for example, S is here, and this is theta of S, right? Or we have S with theta, right? And then if we are interested in the real value, the real value we call P of S, and the imaginary part of S will be of this power we call the Q or reactive power. So we have two types of power, which is the real on the real axis or in the reactive power axis, or we can solve from this representation as well. Cos theta plus J psi theta, right? It is equal to P plus J Q. So P is the real part and Q is imaginary part. Okay. So P is S is V absolute V and absolute I here, right? Q is here. But usually in common practice, we don't use the current in this directly from this relation when we compute the power to represent the direction of the power, right? The direction of the power. Usually we use I in conjugate form, right? We use this amount. So S is equal to V and I to represent the correct direction of reactive power. Usually we put conjugate to I, and this substitute minus right here, like this. Okay, and we call this is the complex power triangle here. Complex power triangle. Okay, so with this representation of AC power, we will have one index called power factor. The power factor is the fraction in between real power and the complex power or apparent power, or S. So the power factor is the ratio between P and S here. We call this is as the power factor. Okay, it means that how much P comparing with S, and the power factor usually less than 1, right? Cannot more than 1. So P cannot more than S. Therefore, power factor cannot more than 1 here. Okay. So I would like to concentrate on or focus on the complex power. Okay, maybe I just skip to the example that help you to know how to solve the complex power. Okay, so for the circuit, I think it's not very important, and it's not very difficult to make understanding. So we just change this value to C equal to R plus JXL, right? And XL is 2 omega F L, right? 2 pi FL, like this. Okay. Okay. Then in the AC circuit, we have also three-phase circuit, three-phase power, and usually we send the electricity in three-phase, right, for the long distance or for the large industrial or large building. We use the three-phase electrical system, right? And in three-phase electrical system, we have phase. Normally, we make a notation as phase A and B and C. Phase A, phase B, and phase C, like this. And each phase will shift to each other by 120 degree, right? 120 degree. For example, if phase A we use as a reference here, right? A reference is here. Phase B we lag phase A by minus 120 degree, and another minus 120 degree, another 120 degree for phase C, like this. So how to calculate the three-phase circuit here, right? Usually we solve by using per phase analysis. We can use one phase like this. We call per phase analysis. Per phase analysis here. Okay. Here in the mostly in industrial, in transmission, in distribution, okay, and in large industrial, large building, or in power generation, mostly in three-phase circuit, right? Three-phase system, electrical system. Okay. And when we solve the three-phase electrical system, we have two types of voltage reference. So first is the voltage of each phase, and next is the voltage in between the phase. Voltage in between the phase. The voltage in between A and B. So each phase will have its own sinusoid signal, right? And for example, this is phase A, right? It says phase A. A into A and the reference, A and reference, or we call neutral in this for three-phase circuit. A to reference can represent into the phasor form also, right? And B is here, right? B, A and B. So the voltage in between A and B during each time is here, right? A and B here, A and B, or A and B, like this, A and B, A and B here. So the RMS value can be solved by the vector between A and B, like this, right? So A and B is here. The voltage in between phase A and phase B is equal to the square root 3 into the voltage between A to neutral, right? A to reference here. And the phase shift would be 30 degree, right? And it shift phase by 30 degree here. 30 degree also, right? Okay. So let's see, when we have three balance circuit, right? And with three balance circuit, for example, this is the motor. We measure the voltage in between phase A and B and C. We call this is V line to line voltage here, and the current of one phase, because it's the balance, we will have the same current for all the phase with the phase shift of 120 degree also, right? We can compute the power of this circuit by square root 3 into V and I, right? Multiply with V and I. In this case, Vi square root 3. This is the power. Okay. And we also have the power factor, right? The power factor is will be P divided by absolute S, or P divided by S in this case. Power factor can also represented by cosine of this angle called theta, because this is P, this is S, and this is Q, right? Or we can use cos theta instead to represent power factor here. Power factor here. Okay. And this is called the complex power analysis, right? Complex power here. Okay. Okay, let's see some example. So in case we have AC motor with the voltage supply of 380 volt. 380 volt mean between line to line, right? Between line to line. Yeah, and this motor draw the current of 50 ampere. Okay, and we measure the power, the real power of 285 kilowatt of this motor. This called single line diagram. Single line diagram. Just to represent the circuit, right? The circuit, right? But in fact, we will have three lines, right? In three phase will be phase A, phase B, phase C into this motor. We have, in fact, the cable is the electric cable will be three phase A, B, C, right? And we measure the current, and we measure the voltage here, right? We have got the voltage of 380 and current of 50 here. So the complex power is square root P, V, and I, right? We know V and we know I. The power will be 329.09 kVA, right? Kilo VA here, kilo VA, and we can compute the power factor because we know that this motor is consuming the real power of 285 kilowatt here. So the power factor will be 0.866 here, right? In this case, we can compute the reactive power also, right? What we can get from this information is the complex power is, or apparent power is 329.09 kVA, and P is 285 kilowatt, and this is the theta with cos theta equal to 0.866 here. Okay, and this is the value of Q, right? With this information, can we compute for Q? Can we compute Q? We can compute for the Q or reactive power. Q we call reactive power with the unit of kilowatt. VA reactive, yeah, right? And we can compute Q in many ways. For example, we can get theta as cos inverse 0.866, and what is theta? What is this angle, right? This will be 30 degree right here. 30 degree. Oh, and we can get Q from maybe S. Q maybe S. Sorry, S and sine theta, right? Sine theta. Oh, 329.09 sine 30, right? Q is S sine theta also. Or Q maybe could be Q is P into 10 theta, or 285 and 10 30 degree. Q is P 10 theta. Okay, also you can get Q from this calculation, or you can get Q from Q can be square root S square minus P square, right? Yeah, by Pythagoras here. then it will be 329.09 square minus 285 square. Like this we can get the reactive value also. Okay, so this is the relation of the complex power in between P, Q, S. Okay, you can get S from volt and M. Okay, you can get P from the measurement value, right? Usually we can measure from the meter. Okay, but the newer meter, you can measure everything. You can measure S, you can measure Q, you can measure power factor as well. Okay, but for the conventional meter, usually we can measure only V and M and ampere, volt and current, and the watt, right, and real power, like that. So if we would like to know the power factor or the reactive power, we need to make a calculation like this example. Okay, let's see another example here, right? Compute the apparent power, active power, and power factor of the three-phase AC balance load. So if we have the load with the terminal voltage of 380 volt, the current is 1000, and real power, we have real power, right? Just similar to this example, right? And we can compute the apparent power or complex power of square root 3V into I, right? Here we have 658.18 kVA here, and we have the real power like this, and we can compute Q by this formula, or in fact we can use this relation or this relation as well. You get the same number, right? Because it's just the triangle law of the triangle, right? Here you get Q value, and you can also compute the power factor. The power factor is the ratio between real power and the complex power or apparent power here, right? Or in fact, S is P plus JQ. In this case, S is how much? 658.18, right? And then Q is 522.686, and P will be 400 here, and this is theta, and the cos theta is 0.608, and you can also compute theta by cos inverse of 0.608, right? So you know this the relation of three power, right? Apparent power, active power, reactive power, or real power. Sometimes we call real power as active power. Okay, here this is the your other homework, but I think maybe to help you to save some time, okay, maybe I just give you this homework only, right? Just do this homework, and this is, you don't need to do, but you would like to do it, you do it for your practice, okay, for your practice. So I will just would like you to be able to calculate the three-phase power. Okay, yeah. This is not difficult, right? Okay, just so this homework. So what is, how many homework we have now? So this is homework number 4, right? Or number 3? I think number 4, right? Homework 4, right? So this is your homework 4. Okay, and I think you can submit this homework after New Year, right? So it should be due date on 3 is holiday, right? So maybe due on 7, right? January 7. Okay, this is your next homework now. Okay, I will stop recording here.